Why are all processes irreversible? Have you ever wondered why things seem to move in one direction? Why can't we just rewind time and return everything to how it was? Today, we will tackle the question of why all processes are irreversible. In the world of thermodynamics, every real process we encounter is irreversible. This means that once a change happens, it cannot be undone without leaving a mark on the surroundings. The main reason for this is the concept of entropy, which measures disorder or randomness in a system. When a process occurs spontaneously, the total entropy of both the system and its environment increases. This increase indicates that energy has spread out in a way that cannot be fully recovered to return everything to its original state. Let's break this down further. When we talk about entropy and spontaneity, we mean that spontaneous processes lead to a rise in total entropy. For example, when heat flows from a hot object to a cold one, energy disperses. This energy loss cannot be completely reversed. This irreversibility is closely tied to finite gradients. Think of a temperature difference driving heat flow. These gradients lead to energy dissipation, like friction or molecular collisions. This dissipation transforms useful energy into less useful forms, such as heat that spreads out into the environment. Once this energy is lost, it cannot be entirely converted back, making the process irreversible. Now, let's consider the microscopic view. While the basic laws of physics allow for time-reversible behavior of individual particles, real systems contain an enormous number of particles. This number is on the order of Avogadro's number, which is approximately 622 times 10 to the 23rd. With so many particles colliding and interacting, the initial states of the system become nearly impossible to recreate. The chance of all particles returning to their original arrangement is so low that it never happens in practice. During irreversible processes, the system often does not maintain equilibrium. It moves through non-equilibrium states where properties like pressure and temperature are uneven. This is different from idealized reversible processes, which happen so slowly that the system remains nearly in equilibrium. Such ideal processes are theoretical and do not occur naturally. In everyday life, this concept of irreversibility explains why machines and natural occurrences cannot achieve 100% efficiency. For instance, friction in engines or heat loss in power plants leads to energy dissipation. This makes it impossible to recover all input energy. To summarize, all processes are irreversible because they increase the total entropy of the system and surroundings, involve finite gradients that cause energy loss, pass through non-equilibrium states, and the complexity of microscopic interactions makes exact reversal statistically improbable. Understanding these principles helps clarify why natural processes have a preferred direction, giving us a clearer picture of the flow of time in thermodynamics.